Hello. First, am I audible? Could you hear me clearly?
Yes.
Okay, then I think we are good to start. So, hello everyone. Myself Kisler. We, the coordinators of the Horizon, are here you to present the story of of a star. So, from its birth to its death. So, me with Ayman, Mridula, and Shruti are going to present you the story of the star. So, uh, just put it in this way. Have you ever wondered how you are made up of? मतलब you are made up of elements and whatever the things. So how it comes in the universe? Have you ever wondered? Is this from the very start? So keep your enthu for the future. Today we are going to discuss this. How these elements get formed and everything. So for today's session, we are going to start with nebula, the birthplace of a star, to the black hole or the death of the stars. There is not only one stage. We will discuss every stages that comes in the star's life, and the death. Is every stars going to be a black hole, or is there any criteria or sort of criterias? So I think everyone is ready, so we can start the session. So I just want to ask the question: have you ever wondered what's the importance of star in our universe? Can you think, even in your life, what's the importance of a star? Can you just write it in chat, whatever you know about this thing? Okay, energy, light in the night sky. Okay, so let me ask the again the same question. See nearby you, anything that is present nearby you. What is it made up of? You can tell it is made up of molecules, and further you will learn it made up of atoms, elements, different carbon, nitrogen, oxygen, uh, aluminum, iron, and many more. But have you ever wondered how these things come in our universe? Is this exist from the very start, from the very start of the what universe, or does this come in the just what processes, different processes that happens in the universe? So I just want to give you just sneak peek. Today you will learn that you are made up of star stuff. The elements that you are made up of was once the part of a star. You were star is basically kitchen of all elements, from hydrogen to iron and whatever you can think of. Everything was once a part of star. Sorry, not hydrogen. Hydrogen is from start. So I just want to rectify this thing. Fine. So star is the kitchen of the what you say, all elements. So you can say that you are already cooked in stars. So no need to cook more. Okay, fine. So as I said, the we will just jump into nebula's thing. So as you know, I say that stars is the kitchen of elements. So that goes with nebula. Nebula is the kitchen of all stars. So basically, when I tell nebula, it is nothing just a giant cloud of dust and gas that is present in space. There is a space where a lot of molecular clouds are present. Molecular cloud of dust, my bad. So it is basically nursery of stars, the starting phase of star. We are going to make star from this molecular clouds of dust and gas. So let me show some pictures, beautiful pictures taken of nebulas. So you can see this whole thing. Can you just see? Is this look familiar with you? This shape, and even its this nebula's name is going to be on this name shape. Can anyone answer this? What it is made? How it's look like in the chat? Anybody? Oh, nice, nice. It's look like butterfly, and its name is Butterfly Nebula. Okay, this one is the most famous nebula that I heard of from my perspective. Can anybody name this nebula? The second one. Okay, fine. This one is Orion one, and the third one is, yeah, nice. Third one is, I think most of you don't know about that thing, but can anybody readily can name this? No, not crab, but crab one is this. This is the crab nebula. This even I don't know before the start of the preparation of this meeting. This is Rosette Nebula, by the way. So you can see the whole name in this slide. Why it's not moving? Wait, wait. Hello, it's something wrong happens. Wait.
Your screen is not
Yeah.
visible, Krishna.
Have
Your
we
screen
stopped the
sharing is
sharing?
Oh, sorry, my bad. I just clicked something wrong. Wait for a sec. Sorry for this. Wait for 1 minute. Okay. It's good now. Is it visible now?
Yes.
Yes.
I just accidentally clicked stop sharing. My bad. I think it's good now.
Yes. You
It's
can
good.
continue.
Okay. Okay, we are here. So you can just see the names. This is butterfly nebulas, Orion nebula, Rosette nebula, and Crab nebula. So let me go into next next slide. So does it look similar? You have seen the shape of this thing nearby you, but I think you see from this. Anyway, uh, can you just write it in chat how it's look like? Yo, cat. It's eye, human eye. So basically, what's point in showing this much pictures of thing? So I just want to say that why nebulas found in ask from you that why nebulas found in these many shapes? Why it's not a simple spherical thing? So the first thing we have to think about is where that molecular clouds come from. That will be a whole different story. We will learn from where that molecular clouds come. But to keep it simple, just assume that we have a molecular clouds from the very start. So the different what will be the different factors that is going to decide the fate of the shape of this nebula? So it's basically how the nebula is going to interact with the surrounding space. So basically, the factors that is going to influence the nebula shape is going to be the one gravitational influence of the surrounding. If there is a star on one place, then some is going to be stretched out. Some region of the nebula is going to be stretched out. And if there is something, what you say, second, is there explosion happening in one part of region of the nebula? Supernova explosion, universe, anything is happening. So the explosion shockwave will carry and what distort the nebula shape. So this can be a possible answer. And one is magnetic field. Since these molecular clouds can have charge, so magnetic field is also going to be decide the shape of the nebulas. So basically, there are all other factors. If a star get formed inside nebula, then it will just clear out that region. So they are very different shape, but the main thing is that the factors that is going to decide our shape is going to be supernova explosion nearby it. One is gravity, another is gravity from the nearby star or within the nebula, and the magnetic fields that is going to be nearby it. So these are the going to be a second the main thing that is going to decide this shape. So as for now, just what the other thing is going to be it's these photos look very eye catching now. So yeah, it goes changing with time as the nebulas proceed. Stars get formed, star gets distorted, the distort the nebulas and gets different story from that. So it gets changing. No, yeah, it can be influence of surrounding, but over time stars get formed now. So formed star becomes his own system, makes his own system, and it gets and with the time nebula disappears. That's fine. That's whole the life cycle. Whatever you want to tell in this. So I just want to ask one more thing. Except shape of this thing, what are the other things that looks very good in this picture? Can we tell what from you? This is very eye catching, by the way. Yo, that's colors. So can anybody tell me how color of nebula is going to be decided? The, if you go in space and look at these things, will this look the similar? The same color, same thing. Okay, nice answer. Nice. Okay. So basically, from where the we just get the what do you say? Colors. So before knowing how the colors is decided, we have to know how the image is going to be captured. I think you learned capturing an image of what stars, stars not celestial bodies in astrophotography session. I think you learned that thing. So basically, this is going to be just a subset of that thing. So basically, how we capture the image of nebula is going to be firstly we have a telescope that can be in space or within uh, Earth from Earth. So basically, telescope capture the image through multiple filters. You can say that infrared. The so filters. The work of filter is going to be it just captured the uh, wavelength of the light that is it allowed to. If infrared is, I'm going to say infrared filter, then it will just allow infrared wavelength of the light spectrum, and it will reject all the other wavelengths. So the telescope work is going to be just it will just capture the image through multiple filters. First with infrared, second with UV, third with H alpha say. It will just capture it, and after that we will do post processing. In that we will just stack all the things, all the H alpha and everything. We will align it properly and stack the things. And after that, we just give color to every filters. You can't see in infrared. That's obvious. Your eye can't see in infrared region. So yeah, it will be in black and white. So this is one of the photos taken by telescopes, Hubble telescope in infrared region. I think maybe some reason. So it looks like the same thing. See, this is Orion after editing, after post processing, and this is Orion before that, taking from only one. So what am I saying? Yeah. So after that capturing thing, we give colors. We decided it infrared region. Okay, we take this from infrared, make it look some dimish red or something. So we do that thing. It's not like it's look like this. We do that thing, but some are true colors. Some of the nebulas have true colors, but these things have artificially made. You can say. So maybe you will go in space and watch these things. Maybe you can be a disappointment. You can get disappointment. But it's not like it's everything false. Information is true about all the things. Okay, now we have talked about the shape and the color of the nebulas. So just summarize the nebula thing. We get a molecular clouds of dust from whatever. We will learn how these molecular clouds come at this end of this end of this session. So we get this. So I will ask, will this going to gravitationally collapse? We have a lot of molecules. They will exert gravitational force on each one, and they will just collapse. This is how it is going to be decided. Is it in this way? Every gas, the group of gases or whatever you say, cloud of gases is going to collapse on its own, or there is some other thing that is happening in the nebula that is stopping its collapse. Yeah, stopping its collapse, whatever you say. So I'm asking the question: is it going to collapse on its own, or there is going to be another factor? Okay, nice. Yeah. Okay, maybe it's spinning. So to know whether a nebula is going to collapse on its own or not, we have to learn the concept of Jeans instability. So basically, Jeans instability is the condition. It determines the condition under which a cloud of gas will undergo gravitational collapse or not. So basically, one force is gravitational force. We agree with that. But many of the nebulas have their own temperature. So temperature brings something that is called thermal pressure. You all know, you all learned this from the 12th class. Temperature will, in short way, I don't want to go in detail, but thermal pressure is something, you have temperature. Temperature will give kinetic energy to the gases so that it can escape easily from the nebula. But there will be equilibrium kind of thing. Gravitation is pulling, pulling inward, and thermal and other factors also there. It's not like only only this thing. What temperature is going to be there? There can be another forces just like shock waves. So there is another force that is countering that gravitational collapse. And Jeans instability is just we are going to give a formula, and it will be your assignment how this formula comes. The you knows this from 12th. You can prove this using your 12th, or most of you are from 12th now. So I think you can prove this using 12th knowledge. So there is something called Jeans mass and Jeans length. So what Jeans mass is, basically it says that if the mass of the region, that particular region of nebula, is going to exceed this Jeans mass, then it will going to collapse on its own. Yeah. So basically, if the Jeans mass of that region is going to exceed this formula, then it is going to collapse on its own. And Jeans length is basically, if you just going to for mass, your mass is going to be constant, you can say. And how much you push, what is the minimum radius of that thing you will push so that it will start its collapse. So these two things are going to be the deciding factor. Why it's not okay? So basically, we have a nebula that is fine, stable. It is not going to gravitationally collapse on its own. So what is going to happen that it starts collapsing? So basically, we have a problem that that region's mass is not enough to collapse on its own. The Jeans mass, it's less. Wait, what? It's not. Is it fine?
I guess it's zoomed in.
I'm trying to zoom out, but it's not happening. Wait a sec. I think it's okay now.
Yes, yes.
Yeah.
Yes.
Okay, so what is going? So our basic is going to be somehow if you increase that mass, total mass of the region, then it is going to start the gravitational collapse. So what can be a triggering event for that thing to happen? Can anybody just tell? You can make your own theory right now. It's enough. Okay, but how supernova? Can anybody tell? It's fine. Supernova is answer one of the answer, but how? Disappearing some mass, nice theory. But how? Oh, nice. Shockwave from supernova, nice. Imbalance of forces, shockwaves coming from it. Okay. It is going to be one possible answer of this. Okay, so our main objective is to increase the mass. So if our nebula is going to collide with another nebula, with a nebula or molecular chunk, with a molecular cloud of dust or gas, the smaller, so it will just increase the mass of that locality or region, so that it will start its own collapse. That is the one possible answer. So second answer can be that supernova shockwave. So basically, how it's happened is supernova shockwave. Supernova shockwaves I say now at the start it will distort the nebula. So density of one side of nebula will increase and one will decrease. That's not our concern. So the increased density part will start its own what? What you say? A gravitational collapse. It will collapse on its own. Start the collapse. So once it gets start, so we will see that nebula will form several chunks in its own. So one chunk is depicting one what star system or any system. So from here, this is going to start its own system, making own system. This will start its own and own. So this is how we are going to. Okay, this is how the what star formation is going to start. So once the gravitational collapse started, so molecular gases will continue to gravitational collapse on its own. Now there is nothing second force that is pushing it outward. At start there is a thermal pressure now, so it can overstand that gravity. But now it's not sufficient, the thermal pressure. So it will just pull inward, and temperature rises. So it keep rising until the temperature will be sufficient to ignite the nuclear fusion. So once it will increase the temperature, it is gravitational collapse. We know from thermodynamics that if something is compressing in the adiabatic kind of situation is there. So once it's compressing, then its temperature is going to rise. So once it's going to rise, it will rise until the nuclear fusion is going to be ignited. So once the nuclear fusion started, our star have something that can withstand gravity. That's nuclear fusion energy. It will get the energy to the molecule so that it will try to escape from the star. So this is how our protostar formed. There is a many thing that is going to be left in this thing. But it's not a proper star. It's just a star. So for next, I will call we will know nuclear fission in detail. So for that discussion, I will ask Ayman to take over my presentation and explain the nuclear fission in detail. So please, Ayman, take that controls.
Is my screen visible?
Yes.
Thank you, Kishley, for that introduction. Thank you, Kishley, for that introduction into stellar evolution and the birth of stars. Now we are going to delve deeper into one of the main processes that occur inside a star during its evolution. So, can anyone guess what is this equation? I'm sure it looks familiar. It's a simple one. Yes, I'm sure most of you would have gotten it right. Even if not, it's fine. It's nothing but nuclear fusion. And here we have two images of nuclear fusion of deuterium nucleus and tritium nucleus, which fuse to give a neutron and a helium nucleus. This is one of the main fusion reactions that occur inside the sun, which is why I'm highlighting it here. Now we are going to define nuclear fusion. The nuclear fusion is a reaction in which two or more atomic nuclei, usually deuterium and tritium, which are hydrogen isotopes, combine to form one or more different atomic nuclei and subatomic particles such as neutrons or protons. So why nuclear fusion is important? The difference in mass between the reactants and products is manifested either as a release or absorption of energy. As we know, in stellar evolution, this is manifested as a release of energy. That's why nuclear fusion is prominent here. Now, just some fun facts about nuclear fusion. Fusion could generate enormous amounts of energy with tiny inputs of fuel and emit zero planet-warming carbon in the process. So here we can see that fusion is a very environment-friendly process. Another fun fact, this is something that occurred very recently, but this is not related to stellar evolution, but since it occurred recently and in the context of fusion, I would like to highlight it here. The scientists sustained a record of 69 megajoules of fusion energy for just 5 seconds using just 0.2 milligrams of fuel. That's enough to power roughly 12,000 households for the same amount of time. So here we can see that an enormous amount of energy can be released from fusion in a very short amount of time using very, very little fuel. So that's one of the specialties about fusion. And the image in the background is the nuclear reactor in which the scientists have carried out this reaction. Nuclear fusion is a process that powers active or main sequence stars. We'll be coming to main sequence stars later, and other higher magnitude stars where large amounts of energy are released. So the reason why the sun and other stars are shining so brightly in the sky is due to this process called nuclear fusion. The energy released is what is the one that's being radiated from their surfaces and cause them to shine so bright. Here we have one of the main fusion reactions that occur in the sun's core. The deuterium and tritium isotopes undergo fusion to release energy in the sun. Now we are going to talk about how fusion happens and why it happens and what are the factors behind it happening inside a system. The release of energy with the fusion of light elements is due to the interplay of two opposing forces. So there are two forces here. The nuclear force, a manifestation of the strong interaction which holds protons and neutrons tightly together in the atomic nucleus. This is one force. And then the Coulomb force, which causes positively charged protons in the nucleus to repel each other. So the two forces are nuclear force between protons and neutrons, and then the Coulomb force between positively charged protons. And now we see how they affect each other. Lighter nuclei, which is nuclei smaller than iron and nickel, are sufficiently small and proton poor. So since they have less number of protons, the Coulomb's force will obviously be less, which leads to the nuclear force to overcome the Coulomb's force. Building up nuclei from lighter nuclei by fusion releases the extra energy from the net attraction of particles. For larger nuclei, however, no energy is released because the nuclear force is short range and cannot act across larger nuclei. So what we are saying here is that in case of larger nuclei, when they try to come closer to each other, there's a large distance between the centers of the nuclei. So, and since the nuclear force is very short range, it cannot act between larger nuclei to cause them to fuse. So fusion generally occurs in lighter nuclei, mostly ones that are smaller than iron and nickel. Did you know? Fusion powers stars and virtually all elements in a process called nucleosynthesis. We'll be coming to that later. The sun is a main sequence star and as such generates energy by fusion of hydrogen nuclei into helium. And this is another amazing thing. In its core, the sun fuses almost 620 million metric tons of hydrogen and makes 616 million metric tons of helium each second. So we can see, considering the fact that 1 ton is around 1000 kgs, so we can see that an enormous amount of fuel is being consumed to give almost an equivalent amount of helium in every second, which is why the sun burns so hot because of this huge amount of consumption and release of energy due to our star process here, which is fusion. And now just some values about the fusion process with regards to the process that occurs in the sun. Fusion of deuterium and tritium creates a helium-4, freeing a neutron and releasing 17.59 mega electron volts as the kinetic energy of the products, while a corresponding amount of mass disappears in agreement with the E is equal to delta M multiplied with C square. So the reason why energy is being released in fusion is because of the loss in mass. So over here, with the sum of the masses of the products is less when compared to sum of the masses of the reactants, which leads to a decrease in the total mass. This decrease in mass is manifested in the form of energy due to Einstein's equation, where E is equal to delta M multiplied with C square. Now we are going to see how the energy is being released in fusion due to the loss in mass. Energy is released in a nuclear reaction if the total mass of the resultant particles is less than the mass of the initial reactants. So energy will be released if the total mass of resultant particles is less. If it's more, energy will be absorbed. So to illustrate, supposing we have two nuclei labeled X and A, react to form two other nuclei Y and B. And the reaction is denoted like this. Particles A and B are often nucleons, either protons or neutrons, but in general can be any nuclei. Assuming that none of the particles are excited and they are in their ground state, the energy quantity is referred to as Q value for this reaction. And how we calculate the Q value is sum of the masses of the reactants subtracted with sum of the masses of the products multiplied with C square. That's how we calculate the Q value for any specific fusion reaction. And the M letters is the mass and C is the speed of light. When the energy value Q is positive, the reaction is exergic. Exergic means it leads to a release of energy. And when Q is negative, the reaction is endoergic, which means energy is being absorbed. As we know in fusion, it's exergic. When both the total proton number and the total neutron number is preserved before and after the reaction, as in DT reactions, the Q value can be expressed in terms of the binding energy of each particle. And what is binding energy? Binding energy is the minimum amount of energy that's required to disassemble a nucleus of an atom into its protons and neutrons. I'm sure it's familiar to all of you. And now we are just going to quantify the energy in fusion and provide some values here. The DT fusion reaction, which occurs in the sun, has a positive Q value of 2.8 into 10 to the power 12 joules. The HH fusion reaction is also exergic with a Q value of 6.7 into 10 to the power 14 joules. And here we can see why fusion prefers to occur in lighter nuclei. Lighter nuclei have a much higher Q value. So fusion occurring in lighter nuclei releases a larger amount of energy when compared to even a slightly heavier nuclei due to the collisions and forces which we'll come to later. 1 metric ton, which is around 1,000 kgs of deuterium, would roughly contain 3 into 10 to the power 32 atoms. So 1 ton of deuterium and tritium would have the Q value of 8.4 into 10 to the power 20 joules. In other words, 1 ton of deuterium has the energy equivalent of approximately 29 billion tons of coal. So, which is why the sun is a highly energetic body in the solar system, which is due to this enormous amount of energy that's being released due to fusion. Now we are coming to one of the important subclasses of fusion reaction which occurs in some types of stars, which is known as the proton-proton chain. The proton-proton chain is commonly referred to as the PP chain, one of the two known sets of a nuclear fusion reaction by which stars convert hydrogen to helium. It dominates in stars with masses less than or equal to that of the sun. So here we can see that the proton-proton chain doesn't occur in all stars, in only those which have masses less than or equal to the sun. Now coming on to the reactions. In PP chain, there are 4 hydrogen nuclei which are combined to form 1 helium nucleus, and 0.7% of the original mass is lost mainly by conversion to heat energy. But some energy escapes in the form of neutrinos. Firstly, we have 2 hydrogen nuclei, 1H, which are combining to form a hydrogen 2 nucleus with the emission of a positron. and a neutrino. And then hydrogen-2 nucleus rapidly captures another proton to form a helium-3 nucleus while emitting a gamma ray. And from this point, the reaction can go into several parts, which we'll be coming to soon. But it always results in the formation of at least one helium-4 nucleus with the emission of 2 neutrinos. The energy of neutrinos emitted is different in different paths, but the most direct continuation is the 2 helium-3 nuclei, which combine to form one helium-4 nucleus with the release of 2 protons. And over here, we can see the different sub-branches of the proton-proton chain and the methods by which it can undergo, and their probabilities too. So as I mentioned, the one with the most probability, which is 86%, is the one where the 2,3 helium nuclei is combining to give a 4 helium nucleus. And also this is the one with the maximum Q value. The Q value is around 26.2 mega electron volts in case of this reaction. And those reactions with lesser probability have beryllium as one of the intermediates. And after that, lithium or boron can also be formed as one of the intermediates. However, they do not form in the products. The products always consist of a helium-4 nucleus. And the Q values of these reactions are 25.66 and 19.17 mega electron volts. So the one with the maximum Q value is this reaction. However, whichever path the reaction undergoes, the net reaction is always this. 4 protons will give 1 helium nucleus, 2 positrons, 2 neutrinos, and the Q value respectively. And now we are going to watch a video about the proton-proton chain.
Let's take a look at the nuclear fusion process that naturally occurs in the Sun and the stars in our truly magnificent universe. Nuclear fusion is the main method used to produce energy in the Sun. Extremely high temperatures and pressures inside the Sun's core provide a setting that is ideal for fusion. The proton-proton chain is a common name for the fusion process that occurs in the Sun. Here are the basic steps of the proton-proton chain. 1. Proton-proton fusion. In the first step of proton-proton fusion, 2 hydrogen nuclei, or protons, collide, thus overcoming the electrostatic repulsion between them. As a result of this occurrence, a proton changes into a neutron by a process known as beta plus decay, emitting a positron and a neutrino in the process. The second proton is unaltered. Therefore, the end products of this reaction is a deuterium nucleus, which is 1 proton and 1 neutron. 2. Deuterium capture. In the second step, a second proton is added to the deuterium nucleus created in the first step to create a helium-3 nucleus, 2 protons, and 1 neutron. A gamma-ray photon is released by this process. This brings us on to number 3. Helium-3 fusion. There are 2 possible routes for the helium-3 nucleus, created in the step explained. These are: Path 1. Helium-3 fusion. When 2 helium-3 nuclei collide, a helium-4 nucleus, which consists of 2 protons and 2 neutrons, are produced. 2 protons, 2 gamma-ray photons, and a significant quantity of energy are released in this process. Path 2. Helium-3 capture. A helium-3 nucleus captures a helium-4 nucleus to create a beryllium-7 nucleus, which contains 4 protons and 3 neutrons. A gamma-ray photon is released by this process. 4. Beryllium-7 decay. A lithium-7 nucleus, which is 3 protons and 4 neutrons, is created when the beryllium-7 nucleus experiences beta- decay. An electron, an antineutrino, as well as some energy, are released in this process. The lithium-7 nucleus does not directly take part in subsequent fusion processes within the Sun after the beryllium-7 decay. As was mentioned in the earlier steps of the proton-proton chain, the primary reactions in the Sun's core involve the fusion of protons to generate helium nuclei. The proton-proton chain, in its entirety, consists of a succession of fusion reactions that change hydrogen atoms into helium atoms, thus releasing energy in the form of gamma-ray photons and other particles. Our solar system receives heat and light from the Sun thanks to this amazing energy.
I'm sure all of you would have gotten a good idea about proton-proton fusion after that video. And now some facts about it. In general, proton-proton fusion can occur only if the kinetic energy, which is the temperature of the protons, is high enough to overcome the mutual electrostatic repulsion. Due to the high pressure, due to the weight of the above layers in the cores of the stars, the protons of hydrogen have enough velocity to overcome their mutual electrostatic repulsion and get within the range of strong nuclear attraction. Another thing to note here is that PP chain is a very slow process. And the reason why PP chain is very slow is since the stars are constantly releasing energy, it takes a high amount of energy to overcome the Coulomb's repulsion between the protons. And two protons must come within the range of 10 to the power minus 15 meters in order for the short range nuclear forces to take control and make the protons fuse. So larger stars which are larger than the Sun have more temperature and pressure, which we'll be coming to. And here is just a time scale of the PP chain. So first, when two hydrogen 1 nuclei are combining, the process takes 10 to the power 9 years. And then when the next step of the reaction, when hydrogen 2 and hydrogen 1 are combining, this takes only 1 second. But when two helium nuclei are combining, this takes 10 to the power 6 years. So therefore, we can see that the PP chain is a very slow process. Now coming to how the energy is released in the PP chain. Comparing the masses of the final helium-4 atom with the masses of the 4 protons reveals that 0.7 of the masses of the original protons have been lost. This mass is converted to energy, as I mentioned earlier, in the form of kinetic energy of the produced particles, gamma rays, and neutrinos, and the total energy is 26.7 mega electron volts. However, this differs depending on the branch which the PP chain takes. Energy released as gamma rays will interact with the electrons and protons and heat the interior of the star, and also kinetic energy of the fusion products adds energy to the plasma in the star. And here we come to this point here. The heating keeps the core of the sun very hot and prevents it from collapsing under its own weight, as if the sun would cool down. So this is related to something which Kishley had mentioned earlier about gravitational collapse. So the fusion and constant energy which keeps the core of the sun hot is what prevents it from collapsing. Now we come to another branch of nuclear fusion that occurs in some higher classes of stars. This is known as the CNO cycle. CNO here is carbon, nitrogen, and oxygen, which acts as catalysts in the reaction. The CNO cycle is hypothesized to be dominant in stars that are more than 1.3 times as massive as the Sun. So high mass main sequence stars fuse hydrogen to helium at a higher rate using carbon, nitrogen, and oxygen as catalysts. Greater core temperature enables the hydrogen nuclei to overcome their repulsion and get within the short range to undergo fusion. So the difference here between PP chain and CNO cycle is that the masses of the stars which undergo them, CNO cycle occurs in stars which have mass 1.3 times that of the Sun. And now coming to the reactions involved in this cycle. Unlike the proton-proton chain, which consumes all of its constituents, the CNO cycle is a catalytic cycle. In the CNO cycle, 4 protons fuse using carbon, nitrogen, and oxygen isotopes as catalysts, each of which is consumed at one step of the CNO cycle but regenerated at a later step. The end product is 1 alpha particle, 2 positrons, and 2 electron neutrinos, but this may differ depending upon the branch which the CNO cycle undergoes. The reactions are as follows. We have a carbon-12 nucleus which captures a hydrogen nucleus to form a nuclei of nitrogen-13 and a gamma ray is emitted. The nitrogen-13 nucleus emits a positive electron and becomes a carbon-13. Now I have a question. Can anyone guess what are these two called? What is nitrogen-13 and carbon-13 called? So they are called as isobars since they have the same mass number. So after that, this nucleus, the carbon-13 nucleus, captures another proton and becomes a nitrogen-14 nucleus and emits another gamma ray. The nitrogen-14 captures a proton to form oxygen-15, and the resulting nucleus ejects a positron and is transformed into nitrogen-15. Eventually, the nitrogen-15 captures a fast-moving proton and breaks down into a carbon-12, thus regenerating the carbon-12 which was initially here to form a helium nucleus, alpha particle, and a gamma ray is also emitted. We now come to the differences between the PP chain and the CNO cycle. The proton-proton chain is more prominent in stars that have the mass of the sun or lesser. This difference stems from the temperature dependency differences between the two reactions. PP chain reaction starts at temperature 4 into 10 to the power 6 Kelvin, making it the dominant energy source in smaller stars. A self-maintaining CNO cycle starts at approximately 15 into 10 to the power 6 Kelvin, but its energy output rises much more rapidly with the increasing temperatures that it becomes the dominant source of energy at approximately 17 into 10 to the power 6 Kelvin. A thing to note here is that although CNO cycle starts at a higher temperature than PP chain, its energy output increases rapidly with increasing temperature. Yeah, like I had mentioned, CNO cycle's energy production increases with increasing temperature. And here we see a between energy rate and core temperature. As the core temperature is higher, we can see CNO cycle's energy is higher. And as it's lower, the PP chain's energy is higher. They have a crossover at 18 million Kelvin. Here, epsilon is the energy released. For PP chain, the epsilon is directly proportional to the power of temperature, and for CNO cycle, the epsilon is proportional to the 17th power of temperature. Now that we've learned about the fusion, we're going to come into another one topic which is related to how the stars maintain their balance, which is hydrostatic equilibrium between the gravitational force and the gas pressure in the interior of the star. This is not visible, right?
Ayman, your screen is not visible.
Yes. Sorry everyone, I'll just come back to it.
Sorry.
Is the screen visible now?
Yes.
So
Yes.
coming into hydrostatic equilibrium, so fusion keeps the stars from collapsing under their own weight, as discussed earlier. Pressure from the outflowing hot gas balances the pressure of gravity. So pressure inside the star acts outwards and gravity acts inwards. This process is called hydrostatic equilibrium. So stars are held together by gravity. Gravity tries to compress everything towards the center of the star. What holds an ordinary star up and prevents its total collapse is the thermal and radiation pressure. Thermal radiation pressure tries to expand the star layers outwards to infinity. So as we can see, the black dots here, they are constantly under motion inwards and outwards because the pressure acts outwards and gravity acts inwards in order to maintain the equilibrium of a star. In any given layer of the star, there's a balance between the thermal pressure outward and the weight of the material above pressing inwards. This balance is what is referred to as the hydrostatic equilibrium. And this can be related to an analogy like the balloon. So in a balloon, the gas inside the balloon pushes outwards and which is like the pressure inside the star. And the elastic material supplies inward compression to balance the gas pressure. So the elastic material of the balloon can be related to the gravity, which acts inwards to balance the pressure. Gravity compresses the star into the most compact shape possible, which is a sphere. And here we see that deeper layers have more gravity compression, so they have greater outward pressure to compensate. And now we are going to see how, as we go deeper and deeper into the star, how the pressure varies. The pressure balance. The pressure at any point is equal to the total weight of the gas above it. Because the star is so massive that the gas inside it is highly compressed and gets very hot. So near the surface of the star, the weight of the gas above you is not very large and thus the pressure is low. But as we move further down into the star, there's more and more gas above you and the weight of this gas is bigger. So pressure is bigger than near the surface. Near the center of the star, the whole weight of the star is above you. So the pressure has to be enormous to hold the star. And now higher pressure is made by higher temperature. Collisions of the particles which move at high speed. So particles which move at high speed have higher temperature, which leads to higher pressure. So that's the reason why it's very hot near the center and cooler near the surface. A thing to note here is that hydrostatic equilibrium controls the reaction rates. A nuclear fusion rate is very sensitive to temperature, as I've discussed earlier. It increases roughly for the pp chain and even more sharply for the CNO cycle. A slight increase in the temperature causes the fusion rate to increase by a large amount, and a slight decrease in temperature causes a large decrease in the fusion. Now, what would happen if the fusion rate speeds up for some reason? The following sequence of things would happen. The thermal pressure would increase, causing the star to expand, but gravity would balance the thermal pressure. But expansion lowers the temperature at the core, so fusion rate would decrease. The thermal pressure would then drop and the star would shrink. Then the temperature, as the star shrinks, the temperature would rise again and nuclear fusion rate would increase. And thus stability would be re-established between the nuclear reaction rate and the gravity compression. So over here, we can understand that if fusion rate speeds up, the star tries its very best to maintain its hydrostatic equilibrium. And now we come to the equation for hydrostatic equilibrium for a star, some math here. So on the LHS, we have dP by dr. So this is the outward elemental pressure by the elemental radius dr. And now we take outwards as positive. So therefore, inwards will be negative on the RHS. And the RHS is capital G, which is the gravitational constant, and M as a function of R. I'll be explaining this later. Divided by the square of the radius and multiplied with rho as a function of R, which is density as a function of radius. Now, the derivation for this is not very important, but we will still go through it quick. And here, this is how we can obtain the mass as a function of R. So the pressure at the elemental radius will be outer minus inner. In case any of you had any difficulty in understanding that, we have a more simpler derivation over here. The diagram is pretty self-explanatory. So mass as a function of R, and we take R as a distance and dr as a elemental spherical shell, and the inner pressure which acts outwards is P as a function of R, and the pressure at the outer surface of the shell is P of R plus dr, which acts inwards, and then we sum up the forces. So force is pressure into area. So, and we take outward direction as positive. So this quantity is positive and then this quantity is negative, subtracted with the gravitational force. And gravitational force is capital G M by R square, a well-learned formula from 12th grade. So over here, the deal is that the pressure that acts inwards, P of R plus dr, can be written as the sum of the pressure that acts inwards plus a small elemental pressure. And substituting all of this in this equation and the value for and the equation of M as a function of R, and then doing some simplification, we can easily get the formula for hydrostatic equilibrium. Thus, when a star is stable, neither expanding or contracting, everywhere within the star, the inward force is equal to the outward force and gravity is equal to pressure. And this condition is known as the hydrostatic equilibrium. However, stars which are forming are not in hydrostatic equilibrium. They are constantly contracting. And as Kishle had explained, during the formation of clumps, it's the clouds of gas and dust are constantly contracting. So gravity is overcoming pressure. So it's not in hydrostatic equilibrium during the formation of a star. Now we come to another important class of stars, which is main sequence stars. What are they? So main sequence is a classification of stars which appear on the plot of stellar color versus brightness as a continuous distinctive band. So stellar color is directly related to the temperature. As higher the temperature, we can see that the color is red, and as the temperature is lower, the color of the star is blue. And brightness is related to the luminosity, as will be explained later. So those stars which are on this band is referred to as the main sequence stars or the dwarf stars. Most stars that we observe in the sky live on the main sequence stars. The star's position on the main sequence depends on its mass. As we zoom in here, we can see how the mass of each star is related to the mass of the sun. So we know the masses of the star, we can then plot this graph. And we know mass by looking at the binary stars. So in the Milky Way galaxy, most stars are either binary or they are in the form of threes. So in binary stars, the mass has a relation to the radius of its orbit. So for binary stars, we can easily estimate the mass and then put them on this graph. So 90% of stars are in the main sequence. Main sequence consists of middle-aged stable stars, and the range is from upper left to lower right, as we have seen on that plot. So upper left stars are large, hot, luminous, and they are referred to as blue giants. Lower right stars are small, cool, dim, and they are referred to as red dwarfs. Main sequence stars, they are characterized by their source of energy. All main sequence stars are constantly undergoing fusion of hydrogen into helium within their cores. The amount of fuel available for star to use depends on its mass. And mass is a huge factor which determines the lifespan of a star. So the total amount of energy that a star can generate through nuclear fusion of hydrogen is limited by the amount of hydrogen fuel that can be consumed at the core. So basically, the more hydrogen fuel available to it, the more fusion it undergoes and the more energy it radiates. Stars on the main sequence remain unchanging for a long period of time. And the reason why that happens is due to their hydrostatic stability. The hydrostatic equilibrium is being maintained in these classes of stars. And now it's a classification of the main sequence stars. They can be classified into three types based on their color and temperature. Small main sequence stars, which are red, cool, and have the temperature of 3000 degrees Celsius to 4000 degrees Celsius. Medium main sequence stars, yellow, white, fairly hot, and their temperature ranges from 6000 degrees Celsius to 10,000 degrees Celsius. So the red ones are ones that are found in the lower right of that plot, and the blue ones are found on the upper left. Larger main sequence stars, blue, very hot, and have a very high temperature of around 30,000 degrees Celsius. Now over to Mridula to continue into the stellar evolution.
Is my screen visible?
Yeah, it's visible.
Okay. So Kishley was discussing about beautiful nebulas, and Ayman was describing about energy fusions and all in the last few hours. So I'll be here describing the most red giants. I mean, the only and the red giants. This is a very particular topic in life cycle of a star, but it's very, very important. So discussing with many of you guys in the chat, I have come to know that you guys know that sun will one day become a red giant. But what if I told you that the sun, the reliable star who nurtured life on Earth, will one day swell into a red giant, shrink again, and become a red giant again? This is like very interesting topic which I'm going to discuss today. But no worries, it will take almost like 5 billion years for it to happen. So can you guys give me any real world example of any red change that is visible in the night sky? Like I have put a picture over here, but I hope you guys guess some names. Yeah, Beetlejuice. Like yeah, wow, there are so many. God, okay, nice, nice. It's Beetlejuice. So it would take a lot of years to burst to form a nebula again, but Betelgeuse is one of the interesting red giants I have seen in the night sky. So, but what exactly causes a star to become a red giant? What is the science behind it? In order to learn all of those, we need the help of H.R. diagram. What is a H.R. diagram? It's basically Hertzsprung-Russell diagram. But wait, don't get distracted by the fancy name. It's just all about the luminosity and temperature graph. To dwell more into the graph, let's see the definition of luminosity and temperature first and learn in depth about the graph. So what's luminosity? It's basically the total amount of energy, or you say the brightness. It's something like that. And the luminosity is given with a formula like relating with the temperature and radius. Generally, if the temperature is high, the luminosity is high. And the lower the size, lower the luminosity. And this is the basic formula for luminosity. And what's the surface temperature? The temperature is basically determined from what is the spectrum of light it emits, right? Hotter the star, more blue it is. And cooler the star, it emits more red and infrared lights. And you might have guessed red means more temperature like that, but it's not like that. Red means it's cooling down, right? So let's delve into the graph. So this is the graph, luminosity and temperature graph. And from the graph, what is the evidence you're getting? You zoom in the graph, you clearly see there are smaller size stars with lower the luminance. You see here, smaller the size, lower the luminance, and larger the size, higher the luminance. And you see even the temperature, it's just 3000 kelvins here and luminosity is very less. And here is 30,000 kelvin and the luminosity is very high. This is like a quite evidence for this relation, right? So, but what are these patches over here, right? Astrophysics is not that easy. We need patches to make it more interesting, isn't it? So we are going to describe and we are going to explain why are these stars deviating from this main sequence into these patches called giants, supergiants, and white dwarfs. And you have seen why is this more interesting? Because 90 to 95% of the stars are in the main sequence. But only a few stars are in giants and supergiants place. So let's see what causes them to deviate from this sequence. In order to learn what is happening, let's first cut the star and see what is inside. Basically, if you take a star like our sun, it has a lot of zones and layers. Each layer consists of different percentage of hydrogen. Like assume this is 40 core is having 40% of hydrogen, and the next layer is having 16% hydrogen. And similarly, there is different composition of hydrogen in each layer. And this 40% is not the exact value, I mean, because it keeps changing. So it's an assumption which I make. Okay. So similarly, in any star, you cut open the star, you can see different layers and different composition of hydrogen. So why am I discussing different composition of hydrogen? The sun needs fuel and it keeps burning hydrogen with the process called nuclear fusion, which was discussed earlier by Ayman. So during this process, suppose the core is having 40% hydrogen and it keeps burning this 40% hydrogen. There will be a certain point where this 40% of hydrogen will be burnt off. That time it takes the hydrogen from the next layers. Let's see what is happening. Basically what happens is that it takes hydrogen from the next layer and the hydrogen shell burning starts. And there is an inert helium core inside here. I hope you see this. This is the inert helium core. And we have seen star always wish for a stability, the hydrostatic equilibrium. So when the temperature keeps increasing, there is a lot of energy is released. It keeps pushing the layers outward. and makes it expand. This is why we tell the sun expands and becomes reaching. But why have I put this mass limit? Why is this limit here? Can any one of you answer this? Why is it's 0.m solar mass and 8 solar mass over here? Chandrasekhar limit. Nice. Yeah, the limits will be discussed very soon. But the basic definition is if the lower the mass, what happens is that it doesn't have enough gravitational pressure, which we learned earlier in the Iman session. It is basically lower the mass, lower the gravitational pressure. So once it exhausts the hydrogen burning ceases, there is no more helium burning. It just becomes a brown dwarf, isn't it? So similarly, if higher the mass, what happens is that there is a lot of gravitational pressure, which is higher than the thermal pressure which is caused inside the star, right? So the core keeps burning, keep till a certain element, like it burns from hydrogen to helium, helium to lithium, carbon, and so on till a specific element. And we'll see and talk about the element in a quite while. But this is the information I want to give her about the mass limit. And about the mass limit, it will be discussed more detailed in the next few slides. Okay, now the core is having helium and the sun is like, I'm more hungry and I want to, burn helium. Now it's already 10 million Kelvin. Though helium is inert, but it is not that inert to hold till 100 million Kelvin. So it starts burning. And this burning actually begins gradually for stars with solar mass greater than 2 to 3. And it begins suddenly involving a process called helium flush. Just like a flash, the helium starts to burn. This happens in stars which are having solar masses less than 2 to 3. And why is this happening? Let's see. So now we are there where hydrogen core is exhausted. The hydrogen core is now exhausted and helium became a degenerate matter. What is a degenerate matter? Basically, degenerate matter is something when it is tightly packed, a material which is tightly packed, and this exerts some pressure called as degenerate pressure. This degenerate pressure is more than the thermal pressure. So it doesn't allow the core to expand further, right? Let's simplify what I have told. In normal stars, the temperature increase, right? And it causes the pressure to increase. And this increased pressure, makes the star to attain a stability and causing it to expand and cool, just like a balloon which is like blowing up. The temperature increase, the pressure increase, and it expands and cool, just like a balloon. But in case of degenerate matter, it is the helium present inside doesn't allow the star to cool or expand. It's just like a pressure cooker, right? The matter inside has a pressure in it, that's degenerate pressure, and this pressure is not allowing it to expand. This is the basic thing. Now, but this doesn't happen always, right? Even if you keep rice in the pressure cooker, after a certain time, it releases, isn't it? Similarly, until a thermal pressure becomes very high, this remains. But if the thermal pressure becomes very, very high, that is extremely high, it exceeds the degeneracy pressure. So what happens? The helium is no longer inert, it starts to fuse. So the temperature increases, more the fusion, more the heat, again fusion. So this is something called as runaway reaction. Now what is exactly happening here? As the thermal pressure increases, the degenerate pressures moves away. That is similar to this. The pressure cooker releases its energy. So this is what is happening. This releases energy and heat and causing it to have more and more fusion. Basically, in stars which are having solar mass less than 2 to 3, this produces a flash which is very, very intense, that lasts only for a few seconds, but the energy released is comparable to the energy released to the entire Milky Way galaxy. and this is called helium flash. But no matter what, in all the stars which is having less than 8 solar masses, I mean the star limit which I have shown earlier, helium finally starts to fuse. So you might have a question, can we witness this helium flash, since I have told it lasts only for a few minutes and a lot of energy is released? Can we witness this? Can any of you tell me, can we witness this actually? Okay. Basically, we cannot witness. It just lasts for a few minutes or so, and it happens inside the core. So unfortunately, it is not visible to the outside world. And okay, now you have seen a star over here that corresponds to helium flash. And see here, now what happens is that, now assume we were here, okay? We were following the main sequence stars and burned the hydrogen, and we were going here, and we started burning hydrogen in for very in a high temperature. So the star seems to expand, and this is the expansion sequence. That's why we got deviated and we went through the red chain branch. We expanded a lot, and suddenly the hydrogen fuel went to the layers, and the helium gave sun a new life, and it gives more and more energy, and it increases the temperatures so drastically that you look here, it was actually around 3000 Kelvin or so, and the temperature drastically increased, and it made it till 12,000 Kelvin. You can look here, but my question is, why is the luminosity constant in this while? And basically this branch is called horizontal branch since the luminosity is almost constant. The temperature increases drastically, but luminosity is constant. Why is that? Why is the branch horizontal? Can anyone answer? With increase in size? You're quite near, but let's see. Basically, it's the opposite. There is a decrease in size. What happens is that one obvious thing is that the temperature is increasing drastically, and the energy is radiated throughout the shell, and this balances the energy which is produced or generated in the helium fusion in the core. So the temperature increase, but the radius decrease. Okay, the size reduces and the energy is radiated throughout the star. Okay, I hope this is clear. And this is why the branch is horizontal. And now, why is this again increasing? And it's called asymptotic chain branch. Why is this called asymptotic chain branch? What does it mean by asymptotic? Something it's almost similar to the red chain branch. That's why it's called asymptotic chain branch. Okay, so now it has raised not because the core was burning, but only with the energy that is produced from helium shell and hydrogen shell burning, right? This combination has produced a lot of energy, and this makes the star to expand again. Now it wants stability again. It's no longer in the degeneracy pressure. The degenerate pressure has decreased and it has gone away. So the star again wants to cool it. So it expands, right? The layers of the star expand again. But what happens to the case of stars with 8 solar masses? As I have told, they have a lot of gravitational pressure. So there is this multiple shell burning happening. Once it has burned from hydrogen to helium, helium burns to carbon, and this produces neon, sodium, magnesium, and this neon burning starts, and which produce oxygen and magnesium, and this oxygen starts to burn, which produces silicon and sulfur, and this silicon burning produces an iron and nickel, and this process stops. But why is this stopping in iron? Why not further elements? Why don't iron burn and give energy to the sun? Sun wants energy, right? Why is that stopping in iron? Can anyone answer why does it stop in iron? Pressure isn't sufficient? Yeah, but after iron it consumes energy, right? And there was one more question. What is the difference between AGP and RGP? So basically, when hydrogen starts to burn, it produces helium and the star wants to cool, right? So it keeps burning and helium is now inert. Remember, helium is now inert and helium is forming the core now, inert core. And hydrogen keeps burning, and helium suddenly at this position, helium starts to burn. And this process is very, rapid. So it produces a lot of energy and the temperature increases drastically, and this is why it causes this leap over here, the horizontal branch. And again, it stabilizes itself and expands again. That's AGP series. First it goes in RGP and descends in horizontal branch, and again expands and cool itself in the AGP branch. I think I'm clear. Okay, now coming back to iron, it basically consumes energy, right? I hope you remember this graph, the binding energy graph. So you see, iron is the most stable nucleus that is having the highest binding energy per nucleon, right? The elements before iron will seems to have nuclear fusion to attain stability, and elements after iron will go through nuclear fission to attain the stability. You might have remembered about the nuclear bombs which have been dropped in Japan. I hope everybody remembers that. That is due to nuclear fission reaction. But absolutely, iron is the most stable one. So in nuclear fusion case, after iron, there is no longer energy is being released. So no more energy, and there is no one to stop gravitation to halt it. And now gravitation is going to take over star. And now what? Now what is going to happen? Well, gravitation collapse, isn't it? But before that, I have a question. We have seen stars with red in color, white in color, blue in color, even in yellow in color. But why don't we see stars in green or purple color? Why don't we see stars in green and purple color? Let me give you some hint. It's due to black body radiation. Can anyone answer why is there is no star that is visible to our eyes that is green and purple in color? Okay then, I guess it's an interesting question then. So let's see. Basically, this is the black body radiation curve. You see here, this is this is at 4,000 Kelvin, this is 5,000, this is 5,000 Kelvin, and this is at 6,000 Kelvin, and this is at 7,000 Kelvin. So cooler the star, we have seen cooler the star, red is its color, and hotter the star, blue its color. And according to the WIPGR color, instead of white, they should be green, isn't it? They should be green, but we have got white. Mm. Okay, then I want to ask you one more question. What is white made up of? What is this white color made up of? It's basically a combination of all colors, isn't it? So you see there is a peak. Whenever there is a peak, that represents the color of the star. Okay. Now you come to the peak of green color star. You see here, there's a peak in green color, but you eventually see there is a equal amount of red light and blue light. So our eyes perceives the green color emitting stars as white color as we receive equal amounts of red and blue light. Okay. And why is there no purple stars? You see, in purple stars, there is a lot of UV rays emitted. It's not just visible light that is there in electromagnetic spectrum. We have UV rays also. So for higher the temperature, a lot more UV rays is being emitted. Right. There was one question like the red chains will release most UV rays. It's not red chains actually. Red chains are cooler. They are very cool. But the blue stars actually emit a lot of UV rays. And when you see, when it comes to the violet color, it actually emits a lot of blue color too. It's just our eyes which don't perceive, and it is very less sensitive to violet color, isn't it? And it is less sensitive to violet and ultraviolet. So we perceive violet color stars or purple color stars as blue color. I hope I'm clear. So now come back to the life cycle of the star, and now I hand over this presentation to Shruti to continue what is going to happen next.
Is my screen visible?
Yes.
Yes.
Is it full screen?
Yes.
Okay, thank you. So thank you, Kishle, Ayman, and Mridula for paving the way for me till the end of the stellar life cycle. Hi, guys. We have come to the end of the stars, their death, the most chaotic phase of their lives. Ever wondered how the death of a star might look like? Well, you're seeing it on the screen. From the left, this is two
Shruti,
new.
your screen is
Shruti,
white, just blank.
white.
The black screen.
Now,
No.
No.
um, now,
Yes, yes.
Yeah,
okay,
it's good.
okay. Yeah, the first one. This photo is two neutron stars colliding, and this photo is we have already seen it. It's the Crab Nebula, which is a supernova remnant, and the third obviously is a black hole. So where there's life, there's death. Yes. But it's not definitely as scary as it was depicted. But yeah, it can be a real threat to humanity. But it can also be beautiful, like the Crab Nebula. But the threat is that it is estimated that a type 2 supernova will be covering the types of supernova later. So, a type 2 supernova closer than 26 light years can destroy more than half of the Earth's ozone layer. So, yeah, it's a threat. Speaking of supernova, no, don't worry. Betelgeuse is about 700 light years away. So if it had gone supernova right now, we won't be seeing it for another 700 years. So yeah, that's enough yapping. Let's get to the actual stuff. What fuels the star and balances the gravitational collapse? We've been seeing it's the nuclear fusion, as explained by Ayman. Beyond iron, nuclear fusion cannot give out energy, but need energy to fuse further, as explained by Mridula in great detail. So, what's next? Gravitational collapse dominates and contracts the star. Oh, so it contracts so much that it becomes a black hole? Well, is it that simple? No. The nature isn't that simple. I'll try explaining Chandrasekhar's limit to a good depth. So, background. Scientists back then were very much convinced that stars collapsing to a point just don't exist. I mean, the idea of black holes were bizarre back then. They tried their best not to get to black holes, even though the math said otherwise. One such scientist was Ralph Fowler. So, Ralph Fowler was certain that according to Pauli's exclusion principle and Heisenberg's uncertainty principle, both of which you all should be familiar with, even not, it's fine. I'll explain. So, according to these two, a star can become a white dwarf and can fuel itself due to the electron degeneracy pressure forever. But Chandrasekhar had pointed out that the maximum speed an electron can have is c, the speed of light, beyond which the electron degeneracy pressure is insufficient, so the star must burst out into a supernova. He had come up with the maximum mass that results in a stable white dwarf, about 1.4 times of the mass of our sun. This is known as the Chandrasekhar's limit. I'll explain it in further detail. Pauli's exclusion principle states that fermions, that are subatomic particles, electron, proton, neutrons, which have integral half spin, cannot occupy the same state. We are quite familiar with this from JE. So as matter is pushed together, electrons occupy their own states and their own fixed volumes and remain stationary. Sounds good. But this violates the Heisenberg uncertainty principle. We cannot know the position and the velocity of a particle at an instant with high precision. We all know this. So the del x dot del p is greater than or equal to h bar by 2. That's the actual equation. This is the simplified thing. Del x dot del v, this one. So since this is there, they cannot have their own fixed volumes and remain stationary. So the more the electrons are confined, the more they are confined, the more we know the position. So their velocity gets higher and higher, and this creates a so-called outward electron degeneracy pressure. Yes, this stands against the gravitational collapse. But even for the electron's velocity, there's a limit, and that's the speed of light. According to general relativity, which we'll be discussing in more detail in the next session on 29th. So the limit for speed of any particle with mass is the speed of light. So even for the electron's velocity, there's a limit. That's what Chandrasekhar had shown. Hence, not all stars can withstand the gravitational collapse with the electron degeneracy pressure. Again, what's the matter that decides this? It's the mass of the star. So if the mass of a star, I mean the stellar mass, not the white dwarf's mass. So if it's approximately less than 8 solar masses, it will become a white dwarf. But if it's more than 8 solar masses, then even the electron degeneracy pressure cannot prevent its fate. So it will blow into a supernova. So this is what Chandrasekhar had pointed out. Before we go to the next part, we'll try calculating the Chandrasekhar's limit with the math that we know as like high school graduates or first years. So let's see. This is a very rough way of trying to calculate the Chandrasekhar's limit. So yeah, let's dive in. So at the Chandrasekhar's limit, we all know that the degeneracy pressure and the gravitational collapse, that gravity are in perfect balance. So that's the very important point that we need to note it here. So yeah, let's consider a spherical white dwarf of mass m, radius r, blah, blah, blah. Let F gravitational be the gravitational force exerted by the white dwarf on its own. That's the gravitational collapse. Then P, DEG, P degeneracy, be the degeneracy pressure of the electrons. So F grav is equal to Gm square by r square. I mean the force exerted on its own. And P grav is like F by A. Pressure is force by area. So that's approximately equal to Gm square by r power 4. And I have assumed that area is kind of like proportional to, approximately equal to r square. So PDEG is now we have to borrow an equation that is the pressure of a Fermi gas. We need not go into the details of how this equation came, but we can just borrow it. That's the formula, h bar c of n by v whole power 4 by 3. So even though and I have to make another point, even though the pressure is called electron degeneracy pressure, the mass of the star would mostly be due to protons. So in this equation, if I have to substitute for n and v, I'll consider mostly the protons mass and volume. So n equal to number of protons, and m be the m is the mass of the white dwarf, and mp be the mass of one proton. So I'm getting n's value as in m by mp, and I'm just substituting it over here, and I'm equating volume again roughly equal to r power 3. So I'm getting the pressure, degeneracy pressure here, and the gravitational pressure over here, gm square by r power 4. So I'm equating these two. So at the Chandrasekhar limit, both will be equal. I'm equating, and I'm substituting the mass of the white dwarf as the Chandrasekhar limit mass. So I'm naming it as MC, and I'm substituting, doing the math, simple algebra. I'm getting MC to be roughly equal to h bar c by g whole power 3 by 2 and divided by ymp the whole square. And that roughly gives to be 1.4 solar masses. I mean, this is a very, very primitive way to find the Chandrasekhar limit, but yeah, why not? We'll try. That's why I put it here. So far, so good, but where black holes? That gets us to the next topic, the Tolman-Oppenheimer-Volkoff limit. In short, TOV limit. So for stars that are even massive, that is greater than 8 solar masses, greater than Chandrasekhar's limit, the electrons and protons fuse to give neutrons and neutrinos. And similar to electron degeneracy pressure, there's a stronger neutron degeneracy pressure. Since neutrons are also fermions, they cannot occupy the same state as well. So the same story goes by. As they are compressed, their velocity grows and results in a neutron degeneracy pressure. But for even massive stars, even this stronger nuclear degeneracy pressure cannot save it from collapsing into a point, and hence they form a black hole. So that's the gist of TOV. Let's get like towards a bit towards the math. So TOV tells us the maximum mass of a stable neutron star. So this TOV limit comes from this equation. This is the TOV equation, and this is like very complex to derive, but it's derived from the so-called non-vacuum form of Schwarzschild metric and the Einstein field equation. So what are these two? First, Einstein field equation is the equation of a general relativity. It's the OG equation, about which we'll be briefly going through the theoretical part of it in the next session on 29th. And the non-vacuum form of Schwarzschild metric means that, first of all, we'll be talking about Schwarzschild metric in the next session. But we'll be focusing on the vacuum form, not the non-vacuum form. So non-vacuum form basically tells that it's inside of the star, and vacuum means it's outside of the star. And we'll be concentrating on outside of the star, Schwarzschild metric. Good. TOV limit basically tells us the upper bound of mass of a star beyond which it ends up in a black hole. If it's below it, it'll become a neutron star after blowing into a supernova. That supernova is different from the supernova of a star above the Chandrasekhar limit. I'll tell you that in great detail when we come to the types of supernova. So stars beyond 25 solar masses will become a black hole. I mean, stars beyond 25 solar masses means that the total solar mass, total stellar mass will become a black hole. And the maximum mass of a stable neutron star is about 2 solar masses. And there's a history for arriving at about 2. Because at first they assumed it to be, not assumed, the math told it to be zero point 0.7 solar masses, which is way below than the Chandrasekhar limit for stable white dwarfs, because they didn't take into account of several physical factors. So after refining it a lot, they have arrived slowly from 0.7 to 1.5 to now about 2 to 2.15 solar masses. So yeah, now we come to the types of supernova. So, in simple words, type 1a supernova results in a planetary nebula, and type 2 supernova results in a neutron star or a black hole. A white dwarf just around the Chandrasekhar limit will explode into a type 1a supernova and become a planetary nebula. This supernova is due to a thermonuclear reaction, but the other type 2, is mainly due to neutrinos. So, stars above 8 solar masses and less than about 10 solar masses, I mean, there's no clear demarcation though, will result in a core collapse supernova, which is also known as type 2p supernova, which we need not go into details because that's not the primary type of supernova that we are going to discuss today. So we'll leave 8 to 10. We'll go for stars above 10 solar masses and below 25 solar masses. So they will blow into a type 2 supernova and leave a neutron star behind. That is, stars below TOV limit will result in a supernova and a neutron star leaving behind. But stars above 25 solar masses will also blow into a supernova due to neutrinos, uh, but leaves behind a black hole. So even the stronger neutron degeneracy pressure will not be able to prevent the indefinite collapse of matter into a single point, like scientists back then were afraid of. So I guess we almost reached the end of a session. Before we go, let's have a quick recap of the stellar life cycle. So Kishle started here, I mean nebula, and then we went through how it goes to a protostar. Is my cursor moving and is it visible?
Yes.
Okay.
Yes.
So we went through, Ayman was talking about nuclear fusion and all. And Mirdula also joined in telling about the nucleosynthesis. And then here is a demarcation. So that demarcation is actually the Chandrasekhar limit. So this is greater than 8 solar masses and this is lesser than 8 solar masses. And we have seen the red giants, red supergiants. We have seen Betelgeuse. So this is our sun. It's a mid-sized, obviously lesser than 8 solar masses. It's 1 solar mass anyways. So if it's lesser than the Chandrasekhar limit, it becomes a red giant and forms a planetary nebula and a white dwarf at the last. So what about stars massive than 8 solar masses? It'll become a red supergiant like our beloved Betelgeuse and hopefully goes into a supernova. But here there's another diversion, I mean, two bifurcations. This is due to the TOV limit. So if the solar mass is lesser than 25, then it goes, I mean, it forms a neutron star. The supernova will uh, leave a neutron star remnant. And if it's greater than 25 solar masses, yeah, it's a black hole. And yeah, supernovas also go to a nebula that is a supernova remnant, Crab Nebula. So yeah, after supernova, they again go to nebula, and the stars below the Chandrasekhar limit will form a planetary nebula at the depth. So yeah, so birth of a star, I mean the depth of a star becomes the birth of another star, and that's why it's a cycle, and that concludes the end of stellar life cycle. Wait, why is it not moving? One minute. Yeah, is it visible? Yeah. So that's not it. We have a whole session on black hole physics. The next session on 29th would be fully about general relativity, black holes, Penrose process, paradoxes, Hawking radiation, and much more. We have covered what a star goes through throughout its lifetime in this session. And one of its climaxes, as we saw, is a black hole. But the climax itself deserves a separate session. And we aren't here to teach you black hole physics, but to pave a way to learn them. So yeah, join us on 29th June for an interesting session on black hole physics. Before going out, I want to add another point. Why should I even learn all these? Some of you in the meeting might ask us. Well, we all know that the answer. We all know the answer because almost everyone present here are curious about our universe, are in awe about how life has evolved from these non-living biomolecules that were formed from the elements, which in turn were formed from stars. And if you are wearing some gold or silver jewelry right now, then probably it had been formed in a supernova. Or if you have copper utensils, then they too would have resulted from a supernova. Every molecule of oxygen traveling in your bloodstream is guided by the hemoglobin, which in turn is bounded by iron, which once was the core of a star. Iron has one of the most stable nucleus in the entire universe, and we use it almost daily. And there's much more. But the one fact that always amazes me is this: in a vast place like a universe, life, that is, matter creating copies of itself, is more than a miracle. Ah, I just can't stand how beautiful life is. And we presenters are so glad to have shared with you our enthusiasm about astrophysics. I can safely assume that people who have been in this session till the last haven't lost their curiosity. Never lose it. Spread the curiosity. In a world driven by possessions, it's the only